So welcome YouTube. For those of you that are familiar with this channel, you know we make documentaries with leading cosmologists about competing models of what happened at or even before the Big Bang. Now, obviously during the pandemic, I've not been able to travel, so we haven't been able to shoot more interviews for our Before the Big Bang series. But today we are incredibly fortunate to be able to host a discussion between two of our biggest stars, perhaps the biggest names in cosmology today. And I'll introduce our guests in just a moment. Now, the idea that the universe underwent an incredibly rapid growth spurt called inflation dominates cosmology today. And whilst most cosmologists accept inflation, some are uncomfortable with the multiverse and infinities it seems to produce. Others have suggested alternative schemes to inflation, and they're often cyclic cosmologies. So do we have to choose between an inflationary multiverse and a cyclic cosmology? I think both are absolutely mind-blowing. So we're so lucky to have with us today to explore these options, the founder of inflationary cosmology, Alan Guth. Welcome, Alan.
Thank you. Glad to be here.
And also inflation's probably most prominent challenger, the 2020 Nobel laureate in physics, Sir Roger Penrose. Welcome, Sir Roger.
My pleasure.
And I believe it's happy birthday. Do you have your birthday this week, right?
Yeah, just a few days ago, yes. That's right.
Okay. Now, of course, we're going to be talking about some of the biggest issues we can imagine. What triggered the Big Bang? Is the universe infinite in space and time? Are there many Big Bangs? But before we get into all the heavy stuff, perhaps, Roger, you could just start us off with how did you learn that you had won the Nobel Prize? Did they give you an inkling? Was it a bolt out of the blue?
Well, it was pretty well out of the blue. I was having a shower and then the phone rang. And that was my PA, Patrona Winton, who said she'd got some mysterious message from Sweden. And should she be allowed to give my phone number to them, which she doesn't normally do, you see. But then we thought maybe she should. And I got phoned a little bit later. I think by then I was more clothed. And I got a message eventually from the president of the Swedish Academy. And he started talking to me, and then he said, well, wait a minute. And he sort of stopped, and the phone went completely dead. Well, I mean, it was dead only because he wasn't there. And so I waited and waited and waited and waited and waited and waited and waited, and I sort of got a bit fed up, so I hung up. But then the phone rang a bit later, and he did reveal that I'd been awarded half the Nobel Prize for physics. And that the other, I don't think he told me who the other two were at that point, because he was still communicating with them. That was the delay. Right. I think he was trying to get through to California, which is, of course, the time zone was a little bit uncomfortable with relation to the timing then. So it was in the morning sometime. I can't remember exactly what time it was he phoned, but it was.
Right. So you won the Nobel Prize for your work on black holes, and that obviously led to the famous singularity theorems that you then worked with Stephen Hawking with. Now, some people have said that these theorems prove an absolute beginning of time, or that physics breaks down at the Big Bang. And others have said, well, it's more of a signpost to new physics. Which would you say it is, Roger?
Well, it's certainly new physics. I mean, people at the time, that the theorem that particularly was what was responsible for the Nobel Prize was something that I did in 1964. It was published in 65. And I gave a talk about it in 64 in King's College London, which was this singularity theorem. It didn't actually, the Nobel Prize was supposed to be for the robust prediction that black holes are, or robust consequence of general relativity. Actually, it wasn't quite what I did. It was to show that singularities are this robust prediction, that if you have a collapse, and so long as you don't have negative energy fluxes, then you're inevitably going to get some problem, which we can interpret as a singularity. This was more or less at the time, just a little later, when quasars had been found, and people were very puzzled about the enormous emissions of energy. Of course, black hole wasn't obviously a source of enormous amount of energy, and it was clear that you could have very wild things going on during a collapse, and as long as it wasn't spherically symmetrical. If it's spherically symmetrical, then you wouldn't get radiation coming out of it, and so what information would come out anyway? So I did have to treat the situation, and it was irregular in shape. That was the whole point. There was a paper in 1939 published by Oppenheimer and Snyder, in which they discussed the collapse of a dust cloud. But the point about this, that lots of people didn't, it was actually a collapse to a black hole, the picture. They didn't describe it that way. But this collapse was very special in two particular respects. One was that there was no pressure in the material. It was what was called dust. And so there's nothing to stop it, if you like. And the other was that it was exactly spherically symmetrical. So everything was focused towards the center. So with no pressure and everything aimed towards the center, it's not surprising that you get a sort of infinite density at that point. But the normal view, that's an artifact, introduce any kind of irregularities and it swirl around and perhaps come swishing out again. And in fact, there was a paper by Lifshitz and Khalatnikov, which had been published, I can't remember exactly when, in 1963 or 64, and they had concluded that in a generic situation, you would not get singularities. I had looked at the paper and I didn't notice, there was actually a mistake, which I think Vilenkin noticed later on, but I didn't see it a mistake. I just wasn't convinced that the type of arguments they were using were particularly robust. And I started thinking about it afresh, using different methods that I'd been playing with for other reasons, which involved completely general space-times and how, if you have a future of a region, what does its boundary look like? And that was a key thing in this discussion.
Right, and that led to the singularities, and then Hawking developed that to the singularities of the Big Bang. And then now Stephen did say, well, this proves the universe had a beginning. Do you think it does prove that?
Well, you see, my views somewhat shifted since that time. I certainly, he picked up, unlike in the movie when he allegedly went to this talk of mine in London, that's not the case. But I gave a repeat in Cambridge, which was a few months later, at Dennis Sharma's request. And Stephen was present there. And in fact, we had a long discussion with Stephen and George Ellis, I think, was there also. He certainly was there. And we discussed the techniques that I'd been using. And Stephen very quickly picked up on these techniques and almost immediately applied the particular theorem I had to a cosmological situation. But that was a rather special case. And then he generalized these techniques, all sorts of developments which eliminated some of the ways out you might have of evading a singularity and applying it to the Big Bang, which is basically, and then we got together and wrote a paper jointly, which more or less covered all the results that he'd had previously. Now, the thing was that with the Big Bang, it was that if you had maybe a collapse before, which then swirled around in some complicated way and then comes swishing out again, that couldn't happen without violating serious energy conditions. So you'd have to have negative energies or something like that, which were very unrealistic to have such a situation. So it more or less showed you couldn't have a bounce which did not have some deviation from standard physics going on. But I was very puzzled about it for a long time. I remember realizing that there are all sorts of singular states you could have, and there are many solutions in general relativity of all sorts of complications. And I couldn't see why the cosmologists didn't consider all these things. And I remember, at a time I was briefly in Princeton, and there was a meeting in Hoboken, New Jersey, which were quite frequent, these meetings, and various cars from Princeton and from Syracuse drive off to this meeting. And I noticed in the back of one of these cars was Jim Peebles. And so I asked him this question. I said, why don't you cosmologists consider all these other possibilities? You just stick with this one simple, very uniform situation. Why don't you look at all these others? And he just looked at me and said, because the universe is not like that. I thought, my God, it's not, is it? I think he was referring to the cosmic microwave background, which is extremely uniform. Right. And therefore, that suggests that the universe was very uniform. So that I began worrying about why the Big Bang was so different from all these other possibilities.
Let me interrupt you a little bit there, Roger. I just want to sort of get Alan involved here. So before we go into sort of all these
good idea.
exciting things about what created the universe to be so homogeneous. Just your take on singularities, Alan. Do you think they tell us the universe had a beginning, or that physics break down, or what do they tell us?
Well, I think the singularities of these singularity theorems are unambiguously theorems of classical general relativity. While I think none of us really believe that classical general relativity is the final word, and certainly under the conditions where one is near one of these singularities, that's precisely where we would expect corrections from some quantum theory of gravity to come in. So I view these singularities as essentially signposts of where we know we have to start worrying about quantum gravity. And since we don't really have a full theory of quantum gravity, the bottom line really is I think we don't really know what happens when the classical theory approaches the singularity.
Right. And you had your own theorem that I keep getting emails about, the Roger Guth and Vilenkin theorem. I presume you do too. People are saying, well, that also proves the same thing as Penrose Hawking. What does it prove?
Yeah, no, that's right. It proves that the expanding era of inflation that we're part of must have a past boundary someplace. That does not necessarily mean the universe had a beginning. And in fact, I don't know if we'll have time to talk about this or not, my favorite picture of the global structure of existence is now something which I really got from Sean Carroll, something that we call the two-headed arrow of time. The idea that the universe is eternal, but that there's a mid-region where the arrow of time is essentially ill-defined. To the future of that, the arrow of time points to the future, but to the past of that, the arrow of time points to the past. So there's a two-headed arrow of time. So the arrow of time is defined almost everywhere except in this mid-region, but points in opposite directions. And there never is a beginning or a real singularity.
Right. So that's obviously, we're going to come on, because one of Roger's key complaints is that inflation can't solve the problem of low entropy. And he's got his own scheme, which we're going to talk about. But before we get to that, why don't you tell us the problems that inflation is thought to solve? Why are cosmologists so excited about inflation? What are these problems of the Big Bang that inflation is thought to solve?
Right. There are two or three of them, depending on how one counts and what one includes. One key issue that had been considered a problem for the conventional Big Bang theory that inflation solves is something called the flatness problem. The question of why the universe is so close to being flat in the sense of Euclidean, especially at very, very early times, because the universe had to have been incredibly close to flat at early times to be even reasonably close to flat today. That's just the way the evolution according to general relativity works. So one way of phrasing this flatness problem is that at about 1 second after what we call the Big Bang, the universe had to have a relationship between its mass density and its expansion rate, which held to 15 decimal places, which means that if you tell me what expansion rate you're talking about, I can tell you what the density is to 15 decimal places. And that's rather extraordinary. And the conventional Big Bang theory required this precise equality to get to where we are today. But there was nothing in the conventional Big Bang theory to explain how we got to that situation. So it seemed like a tremendous mystery. But inflation solves it. Inflation drives the mass density of the universe to just the right value that this condition requires. It's a marvelous solution to the problem.
And one of the others is the origin of structure, right?
That's right. One of the others is the origin of structure. I was going to talk about the horizon problem.
Oh, go for it. Yeah, of course.
Which I think logically comes first. Another key problem is what is called the horizon problem, which is related to the fact that in conventional cosmology, the early universe expands so quickly that the different pieces of it have no time to communicate in any way with each other, even at the speed of light. They really are what is called in physics causally disconnected in the context of the conventional Big Bang model. Yet nonetheless, when we look out at the cosmic background radiation, we see that it's uniform in temperature in all directions to an accuracy of about 1 part in 100,000. Incredible uniformity. But in the conventional Big Bang theory, the photons coming from that way had no way of knowing anything about the photons coming from the other way. Inflation solves that by starting with the universe being much, much smaller than it would have been in conventional cosmology. The uniformity can be established before inflation sets in. And then inflation takes a tiny speck, which has already been made uniform, and stretches it to become large enough to include everything that we observe, thereby giving a very natural explanation for the uniformity that we do observe in the universe. So that's number two. Number three, structure. Our picture of how structure forms in the universe, which I think really does follow pretty much directly from observation, is that the early universe was incredibly smooth. We see this in the cosmic microwave background, smooth to about 1 part in 100,000. But it's gravitationally unstable. Places where there's a slight excess of mass create a slightly stronger than average gravitational field, pulling in more mass, creating a still stronger inhomogeneity. And this process is nonlinear and unstable, and it ultimately causes matter to collapse into stars, galaxies, clusters of galaxies, etc. But the origin of these initial fluctuations had always been mysterious. We knew they had to be there because structure would not have formed without them. But nobody had any theory of where these initial non-uniformities at the level of 1 part in 100,000 might have come from. Inflation, it turns out, offers a very simple explanation for that, a rather mind-boggling explanation, though, I would say, which is that it's all due to quantum physics. At the classical level, inflation would have simply smoothed everything out by stretching it. You stretch a rubber band and it becomes tauter and tauter and straighter. But at the quantum level, it can't become completely smooth. That violates uncertainty principles that the quantum theory has built into it. So where the classical theory would be predicting a completely uniform universe, the quantum version of that theory says that it's almost completely uniform, but in some places it's slightly more massive than others, slightly higher mass density than in other places. Some places the mass density is slightly lower than the average. And that's exactly what the early universe looked like. And the theory even predicts what we call the spectrum of these inhomogeneities, which is the way in which the strength of the non-uniformities depends on what wavelength you're looking at. There are non-uniformities of very short wavelengths, there's non-uniformities of very large wavelengths, and inflation predicts exactly what the relative intensities of those should be for all possible wavelengths. And when we were first calculating these things, which is around 1982, it seemed to me like it was totally fantastical that anybody would ever conceivably measure these things. At that point, even the velocity of the Earth through the cosmic background radiation had not yet been successfully measured. But the technology developed fantastically, and now we have amazingly precise measurements of the non-uniformities of the cosmic microwave background radiation, which show this spectrum that I'm talking about. And the fit between what we see and what was predicted is really just marvelous. So I think most of us now regard that as a very significant success of the inflationary picture.
Right. Okay, thank you for that, Alan. So Roger, you're obviously not convinced by this picture. Why not? What's wrong with what Alan said?
Well, I think the main trouble that I've always had, inflation or no inflation really, is this issue about the difference between the generic singularities which come about from gravitational collapse and what we seem to see in the early universe in the Big Bang, or the result of inflation, if that's what it is. And the view I have is that there's something else going on. Now, why I say this is that if we look at the situations in gravitational collapse, well, the main situation is if you have a black hole, when you have collapse to a singularity. And if this is irregular in some way, then the singularity is going to be extremely complicated. The revised work by Lifshitz and Khalatnikov, where Vilenkin got involved, seems to be much better. And they have a picture of the kind of thing that you can get, a very, very complicated kind of singularity, which is absolutely nothing like the Big Bang. Now, whether you believe them or not, it's certainly going to be utterly unlike it. The best way I can describe this is to talk about the kinds of curvature that you get in general relativity. I hope it's all right for me to mention these ideas.
So I understand there's two types. There's Ricci and Weil. Is that correct?
You see, it's really very important to make this distinction.
Right.
In general relativity, you have this Riemann curvature, which describes the gravitational field, but it also, you have to think of it as being composed of two parts. One of these parts is the Weil part, W-E-Y-L, Hermann Weil, that's named after, and it's the conformal part, so that I'll come to that later. The other part is the Ricci part, and the Ricci part, R-I-C-C-I, was what, according to Einstein's theory, is directly determined by the mass density. The matter, well, it's mass and pressures and various conditions, things to do with the mass density. The matter directly gives you the Ricci tensor. What it does not give you is the Weil tensor. The Weil tensor is separate, and it really describes the gravitational degrees of freedom. Now, to describe what the Weil tensor is in sort of
Can I just interrupt? What do we mean by, I think gravitational degrees of freedom is not a phrase that people will be familiar with. What do we mean by that phrase?
Well, it's easiest to think if we think of electromagnetism, because it's very similar. In Maxwell theory, electromagnetic theory, you have two quantities. One is the charge current vector, which describes the sources. And the other is the Maxwell field tensor. And that describes the field outside. If you have a charged particle here, then outside that, you've got the field. And that's described by the Maxwell field tensor. And if you have radio waves or light, that's waves in this field. And the radiation is all in the Maxwell field tensor. Now, general relativity is basically similar. All the differential orders are different, but let's not worry about that. It's basically similar in that the Ricci tensor is like the charge current vector, that's the source part. And the Weil tensor is like the Maxwell field. So when you get waves, gravitational waves, these are oscillations in the field, but this also describes the field outside a body. So if you have a gravitating body like the Earth or the Sun, then outside the matter, the curvature is the Weil tensor. So that is the field. And if you have a source, which in gravity is the material body, then the gravitational field outside that is given by the Weil tensor. Now, it's also observationally, the difference is pretty clear. The early observations which confirmed general relativity were the bending of light by the sun. And Eddington and other people were able to observe that the light was, when during an eclipse, you could see how the stars were displaced outwards a bit. They're displaced a little bit more near the sun's disk, then a little bit less outside. So they get squashed in the radial direction, but since you're moving out, they get stretched in the angular direction. So if you had a little circular pattern in the sky, that would be made more elliptical. And what you're seeing there is directly the Weil curvature of the sun. It's the effect that the sun has is to distort. You see the distortion of the gravitational waves. In fact, we see this also in clusters of galaxies and things like this, observations. You can see the distortion pretty well directly. You can see the Weil curvature, which is very remarkable.
So what is it about these different curvatures then that leads us to think that we need something other than inflation?
Because it's, what should I say? When you have in a vacuum, you see, the gravitational collapse, the singularity is all in the Weil curvature. And the Weil curvature simply dominates everything. The gravitational wave part, if you like, or the gravitational field part, completely dominates any direct contribution to matter. And that's the natural thing in singularities.
And that would be very messy, is that correct? Sort of
it is extremely messy, yes.
So basically, we've got this messy collapse in black holes.
Absolutely messy, yes.
And am I right to say the Big Bang is very unmessy?
Yes, well, it's messy even in the sort of symmetrical case, that's Weyl curvature dominates. But that's nothing like the messiness that you get in a general situation. Right. Incredibly messy. Whereas the Big Bang was not messy at all. It was very, very smooth and uniform.
And we need an answer as to why.
Yes.
Yes.
And you see, for a long time, like Alan, I had a similar view that, okay, you have to look at the quantum theory of gravity to understand what's happening near singularities, where the curvatures get so big, the radii of curvature get so tiny that you're looking at effects where quantum effects start to come in, and you can't look at the classical picture. So that was a view that I held, like everybody else, and took the view that the resolution must be through some quantum gravity theory. But then I began to worry a lot about the very strong distinction that you get between the singularities and collapse and what we seem to see in the Big Bang. And it's very remarkable because when you look at the early universe, where the cosmic microwave background was created, you go back and back in time until you get, well, it's 380,000 years after the Big Bang, but it's pretty early. And you see this radiation. And it's not only very uniform over the whole sky, but it has this beautiful Planck spectrum, which tells you that you are looking at maximum entropy. So you're looking at completely random. As far as the radiation and matter is concerned, it's utterly random. Now, you see, the second law of thermodynamics tells you entropy goes up and up in time. And it's really very puzzling because you go back and back in time, so the entropy should be going down and down and down until you see a maximum.
So something then is basically telling us that the matter is high entropy, so the gravity must be low entropy.
The low entropy has to be in the gravity, and you can see
the question is, how can we explain that? Alan, let's just go back to you for a sec. There's this puzzle then, why was the entropy so low? When we look at the cosmic microwave background, it seems high. So something must have happened to create this low entropy. Can inflation deal with that?
Yeah, I think so. Well, it does. Just maybe start by saying that inflation is not a theory of the origin of the universe. It's only a theory of the evolution of the universe at very early times. So what actually happens at what classically would be a singularity and what may or may not be modified quantum mechanically is not really something inflation talks about. Might mention quickly that the kind of beginnings that inflationary theorists think about are certainly not analogs of the collapse that Roger is talking about, but rather theories like, for example, the Hartle-Hawking vacuum, where the proposal is simply that the initial quantum state of the universe is determined by a particular condition. There are also theories of tunneling from nothing, pioneered mainly by Vilenkin and Andre Linde.
And I just want to plug our video series Before the Big Bang, because we've interviewed Stephen and Jim about the Hartle-Hawking state and Alex Vilenkin about the tunneling states. If you want to learn more about these ideas, click on the link. I'll put it in the description below for the series.
Perfect. So these do not produce the incredible mess that Roger is talking about. I'm not sure I know anything that could get us out of that mess if that's where we started. But nonetheless, these solutions I'm talking about certainly do not produce a universe directly like ours either. They produce very small universes, universes that involve only a handful of particles. So they need something like inflation to start from there and produce a universe. Now, another view that's taken by inflationary theorists is that the early universe was, quote, chaotic. And that's a rather vague concept. We usually think of it as a scalar field varying in complicated ways with perturbations of the gravitational field that are comparable, but not vastly larger, which I think is what Roger would like. And inflation can work very well in that situation also. This low entropy thing, I think really, I have a very different point of view of from Roger. Any large object that has a huge entropy has pieces with small entropies. We have a universe with a huge entropy. Every photon of the microwave background has an entropy of 3.6, something very small. And what inflation does is it takes a tiny speck of what might be a very complicated, messy thing, probably not as messy as Roger's most messiest things, but nonetheless a very complicated, messy thing with a high entropy even. It takes a tiny speck of that, which has a low entropy, and that's all it needs. It's all inflation needs to then magnify that speck to become large enough to include everything that we observe. I should add here an important feature of inflation that we haven't mentioned is that inflation actually creates mass as it expands. So you start with a mass of the order of a few grams, perhaps, and an entropy that's low because it's a tiny piece of something with a much higher entropy. And then inflation smooths that out and produces exactly the conditions that we want. It should be stated that if one has a positive cosmological constant and inflation acts like a temporary positive cosmological constant, we don't have any rigorous theorems about temporary cosmological constants, but we do about permanent cosmological constants. So if we think of the temporary as lasting pretty long, which is what we think of in inflation, then this should apply. The equilibrium that it approaches, the state of maximum entropy, is a state where the gravitational field is smooth, pure de Sitter space it's called. And the matter entropy is very low at that point as well, because everything has been expanding and the entropy has been thinning out. But then if that cosmological constant or apparent cosmological constant is unstable, which is the situation in inflation, it then decays and produces very high entropy in matter, which becomes the product of that decay, leaving the background metric very smooth, exactly the problem that Roger says he was scratching his head about how to solve. I believe that inflation is a very natural solution to exactly that question.
So Roger, how would you want to respond? And is it time to introduce your own solution to the problem?
Well, not quite yet.
Okay.
Yeah, I have a lot of trouble with this view that you've got, this very complicated, irregular situation, which would be the generic situation, and then you find a little tiny speck where it's smooth enough for inflation to take place, which I gather is the picture that Alan is describing here. Now, the trouble I have with this is that it's so unlikely to get a little tiny speck. It's much more likely to get a somewhat bigger speck. Let me just think. No, sorry, I've got it the wrong way around. It's so unlikely to get a speck which is big enough to create the universe with the uniformity we see all over the place. Much, much, much more likely that you get a little speck which produces a universe which is far smaller. And outside that universe, it can be madness, you see, but the universe, which is nice enough for us to live in and that kind of thing, is far, far, far more probable to find a speck which is small enough that can happen, rather than a somewhat bigger speck, which gives you the entire universe. So I don't see that kind of argument really does explain why we see a universe on the huge scale that we do see, we're just on the basis that we're here somehow. It's a sort of the anthropic argument that we have to be in a universe which has had this expansion, this inflation, and this inflation takes place it's much, much, much more likely to take place in a much smaller region. So I think if you look at the probabilities, I mean, and go back also to the Hartle-Hawking picture. You see, I remember arguing particularly with Stephen on this, and say, well, look, why do you get the smoothed out initial state that they have from the Hartle-Hawking proposal, and this does not apply to the singularities in black holes? I mean, why doesn't the argument apply there? And Stephen's reply was mainly, well, it does in a sense. You have to go all the way back to the beginning. And I thought that was a little bit of not a very good argument. I did talk to Jim Hartle about it too, and I think he was as puzzled as I was about it, actually. But it doesn't seem to me that anything like that does explain why the singularity that we see at the beginning of the universe is on such a big scale, that is to say, the whole universe, wherever we look, seems to be just like what we have here. It's not that it's singled out being nice to house us in a local region, and then it can do what it likes outside. It's the whole thing, which is incredibly more unlikely to find a region that can do that. You just have to, there's nothing subtle about the probabilities here. It's just a huge and absolutely enormous factor.
Alan, is it too unlikely?
Yeah, no, I think there's an important point that Roger is not including in his discussion. We're not talking about just creating a universe as it is now with its 10 to the 89 particles. For that case, everything Roger says would apply. It would be much more likely for it to be half as big or much, much smaller. The most likely thing would be just big enough to house ourselves. But we're talking about the early universe and initiating inflation. And the point is that a patch has to be a certain size in order to inflate, in order for the repulsive force of the gravity of the material inside this little bud to oppose the pressure force pushing inward. So if it's half as big, it just collapses. It must be a certain minimal size in order to begin inflation. And once it begins inflation, how big inflation gets before it ends depends on the lifetime of this metastable state that's driving the exponential expansion. It's not determined by, I mean, any decay is probabilistic, but probability only enters in that sense of determining the decay of a metastable state. So if the parameters are such that the lifetime is long compared to the exponential expansion time, then you get a lot of inflation. And that's the picture that those of us barking on inflation are banking on.
Right. So Alan's basically saying, Roger, that your complaint doesn't quite apply because there's a criteria that the inflating space has to be such a size.
I'd have to see that, but let me not go into that.
Okay.
Yeah.
Well, why don't we introduce CCC then? Because there are a number of competitors to inflation, and we should point out none of them have really captured the cosmological community's love, shall we say. And you've got CCC. We've made a film with you describing it in detail, but let me see if we can summarize it. The idea is that if we get to the far future, at the beginning of the universe, where there's a Big Bang, the temperatures are so hot that we don't have any scale, that you can't build a ruler or a clock. And if we go to the very far future, matter decays, everything decays. So similarly, we can't build a ruler or a clock. So the beginning of the universe and the end of the universe can be matched, and we have this sort of cyclic cosmology. Is that a fair way to describe your CCC proposal?
I mean, that certainly, it needs more detail than that, but yes.
Well, I would encourage people to watch the film that we made with you for more detail.
No, I think they're very good. I think you've done very well with those.
Thank you very much, Roger. So what would you say is the main reason we should take this proposal seriously? Is it the fact that it could explain the low entropy? How does it explain the low entropy, this great mystery of why the entropy is so low?
It certainly does that. You have to look to see where the entropy goes in the evolution of the universe. It goes into black holes. Absolutely. The Bekenstein-Hawking formula for the entropy in a black hole utterly dominates everything else. You don't have to get a very big black hole before that happens. And you certainly see in the black holes that we see, of course, is perhaps a little bit inappropriate term, but we infer that black holes are there, and some of them are really huge. And you don't have to take many of them. Probably even one of the hugest one would encompass most of the entropy in any other form that we see in the universe. So it absolutely dominates everything. That's where the entropy goes, into the black holes. And so, well, what happens to the black holes? Well, according to Stephen Hawking, they eventually evaporate away. And then either a lot of the entropy may go into the radiation, some of it may get lost in singularities, in the singularity in the black hole. It depends on your point of view. Some people think it can't get lost in singularities. Other people, like me, think a lot of it does get lost in singularities. It doesn't actually make much difference from the observational point of view. Now, I should backtrack a little bit, because the entropy is certainly a driving force behind the theory, and the fact that black holes, and therefore we have to ask why the singularities that you get in black holes are so different from the Big Bang. I mean, the kind of argument that Alan was putting forward, that's a different way of looking at the whole problem. In fact, I was impressed by the list of things he mentioned at the beginning. Some of those I certainly have thought about and looked at. I haven't looked at them all. And I think CCC has to address all those questions just as well as inflation does. And I would say also, it's not just that maybe in CCC explains some and inflation sends the other, they are incompatible. You can't have inflation and CCC at the same time. It's not, let me not put it like that. You cannot have the observational features that we seem to see in CCC with inflation. The inflation would wreck the observational consequences.
And so if I understand it correctly, inflation would make the CMB much smoother without any features from any potential previous universe, whereas CCC would see features of the previous universe in the cosmic microwave background. Is that a good summary?
Well, yes, they get stretched out to such a big stage that any tiny effect would be outside our observable universe.
And we'll come on to those observations in a moment. I just want to finish up on the entropy issue. Would it be fair to summarize it as saying that you're assuming that the information in the black hole is lost, and therefore when we get to the next part of the cycle, the end of the universe, all the black holes have disappeared, and so the entropy is in some sense sort of reset to zero, and then we can start again? Is that roughly right?
Yes, roughly speaking. You see, it could be lost in two ways.
Right.
And there's an argument here, and the argument doesn't actually affect this discussion. You see, it could be, there's a lot of it in the Hawking evaporation. So there could be quite a lot of entropy in that radiation. Or it could be because you have the singularity in the middle, and that simply destroys information. Now, a lot of people don't believe that because they think quantum theory will stop it being destroyed. I don't think that works myself, that it is destroyed. But it doesn't really matter, even if it's in the radiation. It doesn't make any difference.
Well, explain to me what happens to the entropy in the radiation? Why does it not become entropy to the next eon?
Because when you match one eon to the next, it is, because it happens so late. You see, the black hole radiation is extremely late. And that means in the conformal picture, I mean, you'd have to see the pictures, of course. In the conformal picture, that radiation always focused at any tiny little point. So in the next eon, it's smaller than the Planck length. So you might think, what about all that radiation? Doesn't that come through? Well, it comes through, but it's so squashed into the next eon because it's so late, you see, because you have to wait 10 to the 100 years or whatever it is. Certainly for the big black holes, you might have to wait something like 10 to the 100 years, Google years. And that is so late that all the radiation is concentrated into a tiny little point as you go across, smaller than the Planck length. So you're really looking at Planck scale dynamics on the other side. And so there's no reason to say that the information is preserved as you go onto the other side. It's more or less just the mass that comes through. The only thing that you can say from the theory with any confidence is that the total mass in that black hole will come through and have an effect on the other side. But the details of that will be completely swallowed up in smaller than Planck scale dynamics.
Well,
doesn't smaller than Planck scale dynamics just mean photons of higher than Planck energy? And I would think that a photon of a higher than Planck energy would be very evident if there were a lot of them around.
No, because these are all at the Hawking points. These are particular points the black holes are localized in certain places. This is where a cluster of galaxies used to be, and that's more or less swallowed up by one black hole, usually. And that single black hole will be one, you see, on the crossover surface, which is because of the positive cosmological constant, you have to have a space-like surface. So it's like a time, it's time infinity, but it's like a time. And at that time, all the radiation, all the information in that black hole is squeezed into a little point. On the other side, it's just a burst of energy. What the form that energy is, maybe in future observations, one will have some clues to what form it has. But it would simply be one burst of energy in that point. And this will be propagated. Photons can't get out because the density is much too great. And they don't finally get out until you get 380,000 years when the microwave background is formed. And that means that that single point is spread out to about 4 degrees across in the sky, which is 8 times the diameter of a full moon. So these spots, which I claim we actually see with very strong confidence level, these spots are what I'm calling Hawking spots, if you like. The point is the point in the crossover surface, spreads out to a spot, which is about 8 times the diameter of the full moon.
So if I just want to interrupt for a moment, so the claim is basically you can see the leftover radiation from the black holes in the previous universe. Yes. I want to come on to those claims about observational confirmation of inflation and CCC in a moment. But Alan, if we can just get a summary of, obviously, well, actually, first off, more generally, there have been a number of competitors to inflation, and inflation is the sort of ruling king of early universe cosmology. How do you feel about people making alternatives? Is that annoying? Is it a genuine thing that scientists should do because we might test inflation is develop alternatives? What's your attitude to this?
Well, certainly my attitude is that thinking about alternatives to inflation is certainly a very legitimate and worthwhile activity and should be encouraged. What I think is also true, though, is that many of the people who develop alternatives also make statements about them which are just not really accurate, and that I don't think is helpful. So honest discussion.
Can you be more specific there, Alan? Come on, that's a leading statement.
Well, for example, when Steinhardt et al. Proposed the ekpyrotic model.
That's the one where we've got 2 brains from string theory colliding, and that triggers the Big Bang. That's the ekpyrotic model.
Right, right. So they insisted that that their original model produced the right spectrum of density perturbations, just like inflation. And immediately several papers were written arguing that that just wasn't true. And about 10 years later or so, Steinhardt admitted it wasn't true. But by and large, there was a long period there where they were making claims that were just unjustified, I thought, and right. I think everybody thought. Right. So that's one example. I also think these circles in the sky are another example, but we'll come to that.
We'll come to that.
I'll try to be
on the theory side. I mean, obviously, Roger, you've got to assume, let's say if I've got this correct, you have to assume that matter disappears in there's no mass in the early universe and in the far future.
When we say mass, we have to be careful what we mean there, because
okay, go ahead.
I mean, certainly photons, and there will be created in the very early universe massive particles.
Right.
So you will get matter in the ordinary sense. Some things come through in the theory, and some things have to be created afterwards. Right. I don't think there's any conflict between the picture that we have and the picture that in the very early universe. Depends on how early you're looking at. If you're looking at Planck times, you see, I think we get away with not having to look at Planck times. I mean, Christoph Meissner.
We should explain the Planck time is the shortest possible time that physicists.
Yes, it's sort of 10 to the minus 43 seconds.
It's a pretty short period.
It's a ridiculously tiny fraction of a time. Yes, fraction of a second. Yeah. Yes. So this would be. I mean, the beauty of looking at CCC is you don't have to look at that scale. You see, you can follow up the classical theory up to a point. I mean, I can go into the details of this if you want me to, up to a point. And this point, according to Christoph's calculation, is just after where you might have to worry about Planck times, things like that. So you can get away with not having.
So this is your colleague, Christoph Meissner in Paris.
Christoph Meissner, yes, that's right. No, so we've worked on well, the latest paper was a paper in the monthly notices of the Royal Astronomical Society, I guess about more than a year ago now.
And that's the one with the Hawking points where there's this radiation from the previous year. Yeah. Well, so why don't we come to the point?
Hold on a second. I would just like to clarify one more point before we go on. It's been said, but I still think it needs to be clarified. Essential to your proposal is essentially a violation of the second law of thermodynamics in the behavior of these Hawking points. You want the entropy, the entire entropy of the radiation that the black hole has produced, and any entropy that might still be in the black hole to just disappear.
Well, it's degrees of freedom you're talking about, and in what do you call it, trans-Planckian physics, we have no reason to believe that these degrees of freedom are preserved. I mean, there is no theory of Planckian physics. So we can do what we like, if you like. But there's no reason to say they are preserved, certainly.
And the degrees of freedom are the sort of number of numbers you need to specify something. Is that the right way to understand it?
Yes. Yes.
And physically understanding degrees of freedom. Alan, do you want to have a stab at explaining what this phrase means?
Degrees of freedom. Well, I think
like physically, like obviously we understand it's the number of numbers you need, but what do we mean when we say, you know, in this context?
Well, we mean the amount of really information, maybe that's the best word that people might understand, amount of information that's contained in the little wiggles of these fields in this region. And the question is that maintained, or does it all just disappear?
Right.
And apparently Roger would like to say it all just disappears. Now, do you consider this a conjecture or something that you can derive from known physics?
No, you can't derive it because we don't have a theory of trans-Planckian physics.
Okay, no, I agree with you.
Yes.
Right.
So it's hard to see what form it could take. I mean, you've just got a mass coming through at that level, and well, what the dynamics of a mass coming through is, we haven't any idea really. I think you don't have to go prior Planck level physics to understand what's happened post the Hawking point. So although the details of what happens are certainly not part of the observations here, it's just there's an injection of a large amount of matter, a large amount of mass energy, if you like. And that mass energy spreads out with the speed of light, if you like, as it can do. And since most of it is probably in the form of very high energy particles, a lot of it's in photons, and they just scatter around with each other. And the sort of analysis that people like Jim Peebles and his company have done in the very early universe would apply here. So the only thing which would be different from the standard evolution would be the actual Hawking points themselves, because the normal analysis would be about the rest of what happens in the early universe. But the Hawking points would be particular places in the crossover surface, or the stretched out Big Bang surface, if you like, which would be different from the other places. And so it would be very interesting to see what implications these things could have, which might go beyond what we see at the moment. People think maybe big black holes occur very early in the universe, and this is a puzzle to some people. Maybe this would address that question. I wouldn't like to say at the moment.
But just to summarize your point, Alan, so basically what Roger's claiming is that we've got this radiation, which he calls the Hawking points from the previous black holes. You're saying they will have entropy, they will have information. And Roger's saying they don't. And that's really
that standard physics would say that entropy is preserved.
There's too much. You're trying to squash too much information into too small a pot. You see, how much information can you get into a Planck scale point? I mean, that's a good question. Are you saying that all the details of what was going on in the previous eon are somehow remembered in that tiny little point? I mean, I regard that as a huge speculation. I don't see why it should be. I mean, you've got the entropy problem anyway. I mean, in the way you're looking at it, you sort of more or less discard those parts of the universe which aren't smooth enough in order for inflation to take place. So you're saying that those parts, I mean, it's not so different from my point of view in a sense, because you're saying those parts don't contribute to the, I don't know, the entropy in the universe. Well, I mean, I guess in the standard picture, it just goes on forever. So you don't even worry about what happens to the entropy in the universe. You start again with, if you're looking at another universe, I don't know what you would say.
Well, that's maybe where we should just talk about other universes and inflation, because maybe, Alan, you could just briefly explain how inflation leads to many universes, and then, you know, what is the similarity then between it? Obviously, people might hear, okay, many big bangs in eternal inflation, many big bangs in a cyclic universe. Are they not perhaps somewhat similar in some sense? So perhaps just briefly explain how inflation leads to this idea of many big bangs, eternal inflation, and then what's the difference between that and a cyclic universe? Okay,
I'll try to do both. And Roger can correct me on the second part. First of all, I should preface this by saying that eternal inflation is somewhat more speculative than inflation itself. My understanding of the sociology of the field is that there are a huge number of people who think that inflation looks very plausible because of its very clear empirical successes. It predicts many properties that we see of the mass distribution of the universe and of the cosmic microwave background. And that does not necessarily involve eternal inflation. But some of us theorists who like to think beyond what we can directly observe, and this includes certainly Alex Vilenkin, Andre Linde, me, and I'm sure I'm leaving out a number of important people. But there's certainly a group of us who like to think about what inflation would predict beyond what we directly observe. And the point is that almost any inflationary model has the property that it produces not just one Big Bang, but ultimately an infinite number of them at an exponentially increasing rate. And that's what we call eternal inflation. It's eternal only into the future. We don't think it's eternal into the past. So the word eternal is not quite being used in its dictionary definition, I don't think. But the way it works is that inflation sets up a repulsive gravity material which drives an exponential expansion of that region. The material reproduces itself as the region expands. And this is basic physics. Nobody really argues that whether this does or does not obey the correct equations of motion. People argue about whether or not it happened, but everybody agrees that this is solid physics as we understand it. And then what happens is this material, this repulsive gravity material, is fundamentally unstable. So it decays and produces ordinary matter and Big Bang universes. But it happens locally, not globally. It doesn't decay all at once. The decay is very much like the decay of a radioactive substance. It has a half-life. But half-life just means that if you wait that amount of time, there's a probability of a half that will have decayed. But decay over here doesn't have to happen, and will in general not happen at the same time as it happens over there. And as these pocket universes form, they expand like some of Roger's rays at pretty much the speed of light once they form. You would think that they would then fill up the space, but meanwhile the space between these bubble universes is exponentially expanding due to the inflation. So in fact, it never fills the space. The space is never filled beyond a certain tiny fraction, really. And that means that these pocket universes will go on forming forever. And each pocket universe, by the way, resembles an open universe as seen from the inside.
Well, can we just define what an open universe is? What do we mean?
Okay, an open universe is a universe whose spatial slices, whose space at a given time is literally infinite, goes on forever. Right. This can happen even if you start out in a finite volume. It's a very peculiar situation, first worked out by Coleman and DeLucia, where one is essentially trading an infinity of time in the future with an infinity of space. So what you might have previously called evolution in time becomes evolution in space.
And that's because in relativity, space and time could be switched from each other.
That's right. Depends crucially on general relativity, where space and time are somewhat interchangeable.
Right.
So that's the picture of eternal inflation. Now, it's often combined with anthropic considerations. Each time a new universe forms, if there's more than one possible type of vacuum, and string theory, for example, predicts that there is, other theories do as well, actually, but string theory is the one that produces the largest number of possible vacua, as far as I know. Right. Each time a new universe forms, it can essentially choose what kind of vacuum is going to be inside it as a random choice, which means that these pocket universes can be rather different from each other. And that leads to the possibility that maybe most of them don't contain life at all and can't, and that life forms only in those pocket universes where it can form. And this gives an underpinning to anthropic arguments that maybe the laws of physics that we see are what they are, mainly because that's what's needed for life to exist in the first place.
Right. Okay, so Roger, I know you've said that anthropic arguments are overused. So could you tell us, when is it okay to use an anthropic argument and when is it not okay to use an anthropic argument?
Gosh, well, I'd prefer not to use it at all.
Okay.
I mean, that's the anthropic arguments, well, as Alan was saying, I mean, if you have an uncomfortable universe which doesn't have the right constants of nature or whatever it is that can produce life, then there wouldn't be any life there, and we couldn't be in such a universe because we're alive, so we've got to be in a universe where life is possible. I mean, that's certainly a logical consistency argument, but I don't like to use the anthropic arguments seriously in physics. I mean, I'm not saying that they have to be wrong. I'm just I prefer to argue not having to use such arguments.
But is that just a personal preference, or is there a good reason not to use them?
That's a difficult question. I tend to think that there are other reasons why the constants are appropriate for life to exist.
What
would be those other reasons?
I don't know yet. Nobody knows.
Right.
I mean, we don't know how dependent on these numbers we actually are. I mean, there's a lot of hand waving in these arguments, and I prefer to steer clear of them, if you like. Put it like that.
Let me see if I can summarize. If I understand what you're saying correctly, is that you're not convinced that we can say we have to have all these values of all the constants. Some people have claimed there's like 24 constants of nature, the masses of all the particles, the strength of all the fields, and so on, and all the forces. And what are you saying that? Well, we don't know whether if we changed them, there would or wouldn't be life. Is that what you're saying, Roger?
Well, I'm trying to say, look, you see, if you're asking me my preferences or my scientific views, it's a little bit different. I mean, what I would like to think, and I think I do think on the whole, is that these numbers are necessarily what they are.
Right, okay.
And that a serious universe in any sense couldn't exist with them being different.
Right, right.
So that is what I like to think. I'm not saying...
Alan, is that a possibility that the constants could just be set by necessity and so forth? There's no sense in which they're improbable?
Well, it could be, but as Roger said, we don't really have any idea how they would be set. In terms of how necessary the parameters have to have these values in order for life to exist, I really have always had the same feeling that Roger described as being uncomfortable with saying that life requires carbon and carbon requires this energy level of that, because we really don't know what other kinds of things could happen if the parameters were a little different. But there is one constant of nature that strikes me as being clearly anthropically relevant and having a value that seems to be very anthropically fine-tuned.
And that's the cosmological
constant. Oh. You got it, the cosmological constant. That's what I was leading up to. Now, Roger may disagree with this. We certainly don't know for sure. But most of our theories, quantum field theory, string theory, really all the definite theories that we have, allow for an arbitrary value of the cosmological constant, with string theory preferring the value of order of the Planck scale, which is vastly larger than anything that we observe.
They like a negative one, which is the wrong sign.
That's right. They would like a negative one, which is the wrong sign. That's also And furthermore, the cosmological constant, at least if we're talking about variations of it of the order of the Planck scale, is hugely relevant to life. If the cosmological constant were some fraction of the Planck scale instead of the tiny value that we actually observe, the universe would disappear in 10 to the minus 42 seconds. And I think Roger and I would agree that probably life can never form in 10 to the minus 42 seconds, no matter what the other parameters were. So to me, the cosmological constant was a touchstone. It's what first convinced me that anthropic arguments might not be crazy. I think we have to admit that anthropic arguments are logical. Roger did too. The only question is how relevant are they? Are there better explanations? Right. And maybe there is for the cosmological constant and other things, but we certainly don't see where it might come from. And,
but Roger, it seems that Alan's agreeing with you that we can't really say these constants are fine-tuned for life, but he'll take an exception with the cosmological constant because physics seems to predict something where we do have a reasonable expectation of what it should be. It isn't that. So therefore, in that case, we can use anthropics?
I don't know. I mean, we just don't know. I mean, Dirac made these arguments, very interesting arguments, trying to show that these constants had to vary. And of course, it turned out he was wrong, but I think the arguments themselves had a certain power. And the idea was, I think the most striking one was the age of the universe in proton times or something. I forget exactly what it was now. There was something, yeah, some big coincidence, you see. And so he thought the age of the universe had to be a variable, because if we lived later, you see, then and so therefore he thought some of these numbers had to change. But then it was shown that you didn't have to use that argument, because the age of the sun depended on these constants. And so the lengths of time were not such a surprise, and they seem to be. But I agree that the cosmological constant, or numbers of the order of 10 to the 60, I guess what you've got there, or 10 to the 120, depending on how you look at it, is a very big number. And where on earth does it come from? Is it a piece of mathematics? Is it just that only that universe like that have people in them or something? I mean, that's the anthropic argument. I like to think that there is some mathematical reason for it. And I don't think I go along with Dirac's original argument that the numbers have to be small. There could be some deep mathematical reason why large numbers come in. And I just have no idea what they are. But that's where I would tend to put my expectations.
Right. Okay. So I want to change the subject slightly. I want to bring up a criticism that's been leveled both at inflation and at CCC by some people I've spoken to. So the criticism is that neither scheme is properly falsifiable. So in the case of inflation, there's sort of two arguments I've heard. One is that there are many different inflationary models. So we assume inflation is modeled with this ball that rolls down a hill, and when it's at the top of a hill, that's when the universe is very energetic and inflation decays. And there are many different shapes for the way the ball can roll down the hill, so that leads to many different inflationary models. And the claim is there are so many different inflationary models that you can't falsify the paradigm, and therefore it's not properly scientific. And I've had the same claim about CCC, that you're claiming there are these points in the sky, these circles in the sky, but if they weren't there, then it wouldn't falsify the model, because it's not a clear prediction of the model. So who wants to go first on tackling these claims?
Well, let me give a comment. See, I don't see that argument at all.
Right.
No, they have to be there, these rings.
Right.
I mean, there's more of a calculation which needs to be done in actually the strength of them. And I don't know quite, we've just been too lazy. The strength of the Hawking points, for instance, one can work very directly and see what the mass was. Now, you see, if that mass comes out to be completely different from the supermassive black holes that we expect to see, I mean, there are certain confirmations that have to be done and have not been done yet, which would be...
What about the sizes of the circles? So can you...
Oh, yeah, there's a maximum size, and that's sort of what we see.
Right.
No, the size comes about from when the black hole collision. I should explain the argument is that our eon, which starts with our Big Bang and ends in a certain sense with our remote infinity, positive cosmological constant being a necessity, unlike the string theory where they've got the wrong sign. So it is actually a necessity that it's positive, because that makes infinity space-like, and so you can join it onto the space-like nature of the next Big Bang. Now, you can see where we are in this conformal picture. We're about 3/4 of the way up. Right. And then if you imagine that in the previous eon, the big black hole collisions took place sort of around about there. You see, we have to think, when do galaxies get to a scale in clusters where they start to run into each other? It's a very rough calculation, but you can do it. Okay. And that calculation leads us to a maximum size of the rings. These rings being in the theory, the gravitational waves from this collision between black holes, and they will come through into the next eon, and you can see the effect in the rings.
Right.
So the rings should be there.
So now many cosmologists have looked at evidence for these rings. Your colleagues, Christoph Meissner, have said, yes, we see them, but many others have said, no, we don't see them. And
no, I don't think that's true.
So just to be clear, if we were to say hypothetically that the ones that say they're not there are correct, would that rule out CCC?
Yes.
Right. Okay.
I mean, I think it would, if it needs a little more detail to see exactly how strong the signals are,
Right.
and so on, which certainly would be a very strong problem. I'll tell you what, it would rule out the version of CCC in which the eons are sufficiently like each other. You could have a version in which there's an evolution as time goes on. I mean, as if you like, conformal time goes on,
right.
And they could be different from each other.
Right.
It doesn't seem so far that this is true, that they do change very much.
Okay.
We don't know clearly, but there does seem a consistency of the kind that we expect to see. I mean, there are sort of calculations that haven't actually been done in detail. I mean, how many Hawking points would you expect to see at the strength of those ones we do see?
Right.
And this is, you only see a very small proportion of them because you see them as our past light cone hits the stretched out Big Bang. And those are the only, a very thin ring of these that you see. That's a certain proportion of the entire lot of Hawking points. And there's a calculation to be done there. I should say most of these calculations have not yet been done.
Okay.
They've not yet been done because we're a very small community,
right.
rather than having large groups of grad students to work on these things, which would, right. Maybe we could get all these things sorted out in no time. But we're busy people, often working on other things
right.
too.
Okay, so Alan, what about inflation? I mean, if the rings that Roger claims are there, would that rule out inflation? Could inflation be ruled out by some observation?
Let's see. There are really two questions. One are the rings, and the other is the general question of falsifiability, right. Which you raised. Well, let me talk about the general question of falsifiability first. It is certainly true that there are many different versions of inflation, which you described well. It depends on what you assume about the potential energy function for the inflaton field. There could be models, there are models with many inflaton fields with more complicated potentials and interactions between them. So there's a wide variety there, but it's exactly the same situation as one has in quantum field theory and how it relates to the standard model of particle physics. There are zillions of quantum field theories. When one builds the standard model of particle physics, one puts in the known particles, one puts in their charges, one puts in their masses. So the model ends up having at least 23 free parameters in its simplest form. And all that is put in by hand to choose a particular, what we call a Lagrangian. The Lagrangian of a theory specifies what the basic elements of the theory are and how they evolve in time. And the same thing with inflation. It's exactly the same thing. Just really what one is choosing is an underlying quantum field theory. Once one chooses the underlying quantum field theory, then the predictions of inflation are perfectly unique, which is exactly the same as test of the standard model. There is a difference in that we can test many more things about the standard model than we can about inflation. So it will certainly take longer to learn more about inflation than what we've been able to do with the standard model. But the basic ideas are the same. Any given model has a definite prediction. Now, what some people are claiming, and I think it's a very small minority, and I think it's really a perversion of what Karl Popper was talking about. I think Karl Popper would be perfectly happy with my version of falsifiability. Any given theory is falsifiable. But some people are claiming, well, you should ask what class of theory these individual theories belong to. And inflation really is a class of theories. And you should ask whether the whole class is falsifiable. Well, nobody ever asked that about the standard model in quantum field theory. And I don't see what sense the question makes. What does it matter if you have a simple way of falsifying the entire class? It's not the way science works. It's not the way it ever has worked or ever will work. Probably if one thought hard enough, one could find a way to falsify the entire class. But I really just don't think it matters. So I consider any model of inflation to be perfectly falsifiable, and that's all we need. Right. And certainly they are testable. Furthermore, maybe I should emphasize this as well. There's certainly a class of inflationary models. Single field slow roll models is a technical designation, which make very similar predictions. They predict that the universe should be flat. They predict that the cosmic microwave background radiation should be extremely uniform. They predict that the non-uniformities should be essentially scale invariant. same intensity on all scales. They predict that the non-uniformities should have what's called a Gaussian probability distribution, which is a particular technical thing about how exactly the probabilities behave. Essentially a generalization of the famous normal bell curve. And all of those have been verified. And they're non-trivial. And I guess I didn't even say them all. It also predicts the perturbation should be what are called adiabatic. I won't go into what that is, but it's, again, a very precise prediction verified by observation. So inflation has a tremendous amount going for it, which is why I think the community is so heavily invested in it. And
then what about the rings? Like, suppose Roger's rings were confirmed. Let's suppose the CME community said, yes, we see them. Does that rule out inflation or not?
Yeah, definitely not. There have been about 8 papers that I noticed looking through the list, through the literature that have criticized Roger's papers. There have been no papers written besides the 5 original authors that I was able to find who confirm Roger's findings. The papers that criticize Roger's papers all have a common theme, which is that, yes, these things are there. But if you simulate inflation correctly, and the insinuation is that Roger and his team have not been simulating inflation correctly, but if you simulate it correctly, these things are exactly what inflation predicts. They're just random fluctuations. And paper after paper after paper, well, 8 of them have reached these conclusions. And for that reason, I think, most of the world has not been paying that much attention to the claims that Roger and his colleagues have made about these circles in the sky. And as far as I can tell, that is the situation, that the teams that Roger has been working with have not been correctly simulating what inflation predicts.
So Roger, how do you want to respond? You're not simulating inflation properly.
Well, first of all, it should be made there's 2 completely different classes of observation here. And to talk about rings in one sentence is completely misleading, because the Hawking points are completely different effect. And I know a paper which was disproving it before our paper had even come out. It was only in earlier versions. This was Douglas Scott and a colleague. And the analysis done there seemed to be completely, there are lots of ways of not seeing them by doing the analysis in another way. But you have to do the analysis right to see them. And that's certainly correct. But I don't see anything wrong with the way that the analysis is done and in Hawking points. I haven't seen anything which contradicts it. I don't know what Alan is referring to here. I think he's talking about the rings, which are the earlier signals, which I can't see how inflation predicts. You look at some of these. You take the pictures from the Planck data, where Vahe Gurzesian looks for low variance rings where you look at 3 concentric rings of low variance, and then you plot them in the sky, and you plot them also due to the average temperature. They're chosen for the low variance, not for the temperatures, for the variation in temperature. And you see a very, very non-uniform distribution over the sky. And whatever explanation for those spots is, it cannot be inflation, because inflation doesn't have this grossly non-uniformity over the sky. A striking feature of this is that you look at the non-uniformity of the distribution, and then you look at the color. Now, the color is giving just the color.
When you say the color, do you mean the differences in temperature? So like there's one color to one temperature, another color. Right.
And you see that this is an independent parameter. Because they're only selected from low variance, not from the color with the temperature. But then you see they are clumped in just by color as well. And in CCC, there's a clear explanation, because you're looking at a very big clump distribution, and the color is an indication of how far away they are, and the angular distribution is, how that dimension, and the color is that dimension. So what you see is that they are strongly correlated in distance as well as in location in the sky. Now, somebody else needs an explanation for that. And it's certainly not inflation, because inflation gives you a uniform distribution. There may be some other explanation. Sorry?
That's exactly the error that everybody is accusing you of.
Right. Well, no, whatever. Tell me a paper that's addressing this particular.
Inflation gives you a what's called a Gaussian random field.
This is not
a Gaussian random field does have correlations between one point and another. It is not just a uniform distribution of every pixel having the same probability distribution. And as far as I could tell, you've never recognized that. And that's why you're always making statements that the inflationary community is not buying.
Don't think we
so to give you some concrete examples of the literature, you said you're not aware of these papers. I don't know. But one of the things you claimed was about this non-uniformity of the locations in the sky. That calculation was exactly done in the paper by Zhao and Scott in 2019.
Douglas Scott again?
Douglas Scott again, right. Douglas Scott is an authority. He's one of the authors of the reviews of the review of the cosmic microwave background and the particle data group reviews. He's certainly highly respected, and he knows what inflation predicts. And he's right. I'm quite sure.
I would be
so he looked at the distribution of points where these circles are seen. Nobody denies that they're seen, by the way. That's not the controversy. The question is, are they seen at a level that would not be expected in inflation? And all of the papers are concluding that they're seen at exactly the level that would be expected as random fluctuations.
I would be very surprised.
And the point is that as long as you have correlations between points, you do have the possibility of clustering. The distribution is still spherically symmetric in the sense that the probability of any configuration is the same as the probability of the rotated configuration, but there still is clumping. And the relative positions of these things on the sky was tested for in this paper by Zhao and Scott, and they concluded that it was just right.
Well, I know that some of these papers, the analysis they do is doesn't really hold together. I'm thinking about the ones on the Hawking points. I don't know about the one on the rings.
Well,
I know that the paper that they initially, no, because I know I met Douglas Scott at a conference in Princeton, and I was quite pleased to hear that he wanted to repeat the analysis that Bahir had done, and eventually did repeat the analysis and saw very much the same distribution that Bahir had seen, which was a relief to me because I had no idea really. I was glad to see that he sees exactly the same locations, but then the argument was trying to be that this is something random.
Yes, that's the argument.
I find that really hard to believe.
So, Rich, if I want to sum up, the disagreement is these points are there. We all agree on that. The circles are there. The question is, should they be there given a random distribution? Or should they not?
Given a random distribution with the probability distribution dictated by inflation.
Right.
The word random, it's important that the word random really has no meaning until you specify a probability distribution.
Right.
We're not talking about random in the sense of every point being just a random variable.
I see.
That's not what inflation predicts.
Right.
And that's not the random that inflation is talking about. Inflation is talking about what is called a random Gaussian field, and that does include correlations between points, depending on the distance between them. And that's what it seems that Roger has left out in his attempts to describe what inflation would predict.
Okay, so I want to move on. We're running out of time. So I want to move on just a couple of topics. One topic that I think you both agree on, and you can both defend yourself against criticism from outside. And that is this issue of infinity. So as I understand it, correct me if I'm wrong, both CCC and eternal inflation have infinities in them in the sense that the universe is spatially infinite and there's infinity in time as well. Now, some people, David Hilbert said infinity is nowhere to be found in nature. George Ellis has recently said, you know, we can't have infinities in nature. And I think there's sort of two arguments that have been presented. So one is that if we have infinities, we get absurd conclusions. So we could have famously Hilbert's hotel, where if we have an infinite hotel and it's occupied, we could still admit more guests. And that seems a contradiction. How can a full hotel admit more guests? So then we have these absurdities. And the second argument is, well, we can't count to infinity. If we start 1, 2, 3, 4, 5, 6, we will never get to infinity. We'll just get an always bigger and bigger number. So would I be correct to say both eternal inflation and CCC allow infinities? And what's your response to these criticisms from people like Hilbert, George Ellis, and others that we can't really have infinities in nature?
Which one do you want to speak first?
Okay, so Roger, why don't you start with the absurdity of a Hilbert hotel, that you can't...
It's not an absurdity, it's just what happens if you have infinity. I mean, that was the major thing that Cantor had showed. You can talk about infinity in a serious way, and you deduce very powerful results from talking about infinity in the right way. You have to be careful when you talk about infinity, but yes, if you're careful, talking about infinity is perfectly reasonable. I think, you see, CCC deals with infinity in one sense. You see, the actual time of an eon is infinite. But you see, what does it mean? Because when you start to lose mass, you can't really build clocks, and then does that time actually mean something you can measure? But then you have a way of transforming it so that it becomes finite. And if you look at it in terms of the whole picture, and you look at what people in the next eon would look, they see finite things. So I can't see a general statement about infinity is not physics or something. I think Hilbert was going a little over the top there, if that's what he said.
And then what about the argument that, because you as when we've spoken before, Roger, you've said you believe that the eons are symmetric, they're eternal into the future and into the past. And some people would claim we can't have eternity into the past because we would never get to now. You'd have to count infinitely more. And you can never get to now, as it were.
An absurd argument. I'm not even saying it is necessarily infinite.
No,
and that's the simplest model.
Right.
You know, if there were 73 eons, and that's the answer.
Right.
Okay, well, that would be a little bit harder to believe than infinity, I think. You know, if there are 3 of them and we happen to be in the middle one or so on, I don't know. It doesn't require that the sequence is infinite. It's just the simplest description.
Right. But what's absurd about saying, well, we'd never get to now? What's wrong with that?
I can't see the argument. I mean, you could say we never get to, why am I here in this spot rather than this universe is so vast? It doesn't have to be infinite, you see. I could be, right. But I mean, you know, you've got to have an evolution which evolves in a sensible way, and you're around places where there are other people, and I don't see the argument, quite honestly.
Alan, what do you want to say about this?
Yeah, well, I guess I'd maybe elaborate a bit about not seeing the argument. I think what Roger's probably thinking is what I would think is that there's certainly a well-defined mathematical description that one can imagine where there's some function that's defined for all time that describes what's happening at all time, maybe a wave function that evolves with time and is defined for all time. How did we get to now question really just doesn't arise. At the time T0 that we call now, the wave function says that certain things are happening. And if that's an accurate description, that's what's happening. One doesn't have to start at the beginning at minus infinity and go through all the times to get to now. One is just here now.
Right. So in fact, I asked Abhay Ashtekar this, who is one of Roger's postdocs, and he's obviously now the sort of head of the loop quantum gravity community. And the analogy I gave was, well, imagine you have a race. You're going to count down from 3 and start the gun. And okay, we're going to start the race when I've count down 3. If I say I'm going to count down from infinity and start the gun, you'll never start the race. And what Abhay said to me was, there is no gun that started. So there is no first moment, obviously, if the universe is infinite to the past. So the problem doesn't arise. Is that what you're saying, Alan?
Yeah, I think it's a version of that, yes.
Right. And is that something you would agree with, Roger?
Well, I suppose I'm not quite sure I see I'm not even got as far as understanding the argument, actually.
Okay. Well, let's wrap up with one or two last things. And this is the statement that multiverse and cyclic universes are both sort of beyond what we can see, and therefore they're too speculative. Either are too speculative to consider as science. What would you say to that, Roger?
Well, I mean, we talk about the universe as the standard cosmology that we've just been hearing about. I mean, you talk about it being flat, and that means it goes on indefinitely, spatially in all directions. I mean, we can talk about it without being surprised that somehow we are here rather than, I know, I mean, you've got an infinite location at different places. I can't really see that argument either. I mean, it may be infinite, it may not. I don't think we have to believe it necessarily. It could just be very, very big and not necessarily spatially infinite.
Right. And what about you, Alan? Is the multiverse too speculative? I mean, you must have had that thrown at you a few times.
Right. Well, I think if somebody wants to tell us that it is speculative, I don't think we should argue with those people. I think it is speculative, but I think it nonetheless is what? Too speculative. Right. Okay. I believe it's speculative, but not too speculative. That is the description I would give. And the reason is that it does connect to questions that are real. It connects, for example, to the question of how do we understand the value of the cosmological constant? If we have to explain it by mathematical means, saying that that's the only possible value, that would be one thing. And Roger would like that to be the case. I would like that to be the case too, except I think it probably isn't. But the idea of a multiverse does offer an alternative, which I think is a very real alternative in the sense that it's perfectly logically consistent. Furthermore, the same models of inflation, if one takes those seriously, which I of course do, the same models of inflation which allow us to calculate all the properties of the cosmic microwave background, almost all of those also predict that if you take those models seriously, it will produce a multiverse, and not just a single Big Bang. So the properties of the multiverse become entangled theory-wise with theories that we build to simply describe what we directly see.
Right. Okay. And then lastly, let's look to the future. There was a scare, of course, in 2014 that it had been detected primordial gravitational waves, and it turned out, that was a bit overblown claim. It didn't quite stand up. If they are detected, some people will say, that would really confirm inflation done. Whereas CCC, I presume, would it rule out CCC if those were detected?
No, you have to look very carefully at what the signals actually say, because they might be primordial magnetic fields, for example. And CCC predicts that there should be primordial magnetic fields because they will be in galactic clusters, and they will probably at a certain stage, if the mass fades, you would get them to spread out a bit. So somebody has to do a calculation to find out how strong, where, how big these primordial magnetic fields are, and they would certainly produce B modes. So I can't see that it's a strong yes or no at this stage.
Right, but that would depend on there being magnetic fields, primordial magnetic fields.
Yes, it would be very nice. You see, when I say we're a small community, I really would like somebody to do that calculation. What does CCC really predict about the intensity of primordial magnetic fields and how strong, where, how big, and so on? Maybe these are things that could be seen in people who look for B modes. So it's not a very simple story here. I would say you can't say, look, this is a direct indication of inflation. No.
Okay, Alan, what do you say to that? If we found these primordial gravitational waves, Roger's saying, well, they could be from primordial magnetic fields, and so not necessarily from inflation.
No, they wouldn't. This, I think, let me correct something here. You see, this is not a question of primordial magnetic gravitational waves. It's B modes.
Sorry, yes, sorry, my mistake. Yeah. So if we found this signal in the microwave sky,
that's right,
that are this wavy pattern, it could be from primordial magnetic fields, is what you're saying, rather than
primordial gravitational. But you see, there could be primordial gravitational waves also. I have never done the calculation to see whether they are of any sort of scale that you would see, because you have you have gravitational waves. Of course, you've got the ones that LIGO sees, but there will be lots of smaller events which will cause a sort of background of gravitational radiation. So there will be a background. Is that background far too small to see? Or is it something you might make a prediction about? I have no idea. I haven't even looked at it. But there are questions like that. A lot of questions that should be looked at with CCC. In fact, I'm a bit surprised that Alan didn't bring up the scale invariance of the microwave background, which I always thought was one of the big arguments for inflation. And then you have to see why CCC also predicts things like that. I mean,
I think we've run out of time, but you can watch our film on eternal inflation, and we talk about the scale invariance of the cosmic microwave background. But Alan, do you want to address that point about, if we do detect these B modes, could it be actually from something other than inflation?
Well, I think it's pretty hard to rule out all other possibilities. And right now, inflation is maybe the only theory that's made very clear prediction about the properties that these B modes should have, and maybe the only theory that's made a very clear prediction that they should exist, except I should mention that while inflation clearly predicts that it should exist, the level at which they should exist is hugely variable among inflationary models. So it could literally be 20 orders of magnitude below what we can detect. So inflation is not really predicting that there should be detectable gravitational B modes, only that they should exist. So I think if B modes are found, I'm sure there'll be several years of arguments about other ways that maybe it was produced. My guess is that inflation will hold up as being by far the most plausible way that it could have been produced.
Right. I just want to add that actually, when we made the film with Alan, we did talk about a possible other way to generate B modes, which was string gas cosmology. But there is a way to distinguish between the two. And if you watch the film, you'll find out what that way is. But I will leave that for then. So maybe we should just sum up where we are, and then we'll close the discussion. It's been absolutely fascinating. I want to thank both of you. It's incredibly generous of your time. So Roger, do you want to just sum up? Where do you think we are with early universe cosmology about conformal cyclic cosmology versus inflation? How do you want to end things?
Well, CCC is very much in the infancy with regard to observations. And I think there are a lot of things that could be looked at which have not yet been looked at and worked out, and lots of ways that the theory could be falsified. I think that's absolutely right. However, if these things keep being confirmed, then we have a problem with inflation, because inflation is really inconsistent with CCC. If you have an inflationary phase, that would wipe out all the signals which would confirm CCC. So I think there is a big conflict between the two views here. And we'll have to see to what extent one or the other comes through.
And Alan, how would you like to sum things up?
Well, I think there are certainly important questions about inflation to be answered. Inflation is not a unique theory by any means. It's a class of theories. And there's a lot to learn about trying to narrow down that class. Concerning these signals that Roger spoke about, I don't believe what he said. There are at least 8 papers in the literature that have looked at how well these signals can be accounted for in inflationary models, and they don't find any incompatibility at all. And the structure of that inflation predicts for the cosmic microwave background is much more complex than just choosing every pixel randomly, which seems to be the model that Roger and his collaborators have been thinking of as describing inflation. So I think inflation is certainly compatible with the existence of these circles that have been seen, and the other evidence for Hawking points that have been pointed out.
Okay, well, thank you so much, both of you. It's so kind of you to agree to this. And for those of you watching, if you have any thoughts, please put them in the comments. And if you'd like to see more discussions like this, again, mention it in the comments. And thank you everyone for watching. Thank you, Alan and Roger, for taking part. It's really great. And I wish you all a great evening. Thank you very much.
Thank you.
Bye-bye.
Thank you.